mode of heat transfer: conduction, convection, and radiation. And in these cases, we have not dealt with any type of forced, like something is applied externally to increase the flow of heat or temperature, and in forced convection we will see that some external device is used for the transport of this type of convection. Okay. So something is used to force the heat transfer, so that is called forced convection. And you can also read all this. This is the basic difference: free convection and forced convection. Okay, so this is the basic difference: free and forced convection. Okay, so this is the basic difference when the flow is naturally and when the flow is forced by some means. So this is called forced convection. Okay, so further we will go through, and you can read what is boundary layer. Boundary layer, you already know the type of if you know the type of flow, like here is the stationary boundary, and like if you tell you there is a some plate. Okay, this some plate, and let me choose some other line. Okay, there is a plate, and there is a plate, and some flow. It's making some irrelevant thing, so I must let me choose some other options. We will take this is not happens. No, not working. Okay, here you can see this is the stationary boundary, and some fluid is flowing on this plate, and due to flow of the moving fluid, there is a variation of velocity, and at the surface of the boundary layer, at the surface of the body, velocity will be 0, and at some extent from the boundary layer, velocity will be the free stream velocity. Okay, so you can see here, and this is the boundary layer, and we will study everything inside the boundary layer, because our concern is about how the flow is flowing and what are the changes happening in boundary layer. Okay, so you know shear stress tau is equal to mu du by dy, where mu is the viscosity. Okay, and u is velocity and y is the perpendicular distance, and here you see velocity variation. Okay, fluid flow, and here in boundary layer you can see velocity is varying direction of y, this direction. Okay, as we go up, velocity will changes time by time, and at some extent it will become free stream velocity, and outside the boundary layer it is called as potential flow. Okay, so just remember this formula, and it is important. And viscosity dimension, it is also important. Kg meter per meter second. Okay, this is the important formula you must remember. And next, this is the case of turbulent flow, laminar flow, and streamline. The streamline is parallel, and they do not intersect each other. And, in turbulent flow, there is a flow zigzag pattern. Okay, so here, and it is decided by the number called Reynolds number. Like Reynolds number is rho v d upon mu. Like if you draw, just draw. Okay, here is the Reynolds number, and based on the Reynolds number, decided that okay, based on Reynolds number, it is decided that it is a laminar flow, turbulent flow, or transition flow. Right? If Reynolds number is less than 2300, and this the flow is called laminar, and if it is more than 23,000, it is called turbulent. And somewhere you can see it is also written as 4000. Like in 2300 to 4000, it is called transition. Okay, here you can see flow over a flat plate. flow over a flat plate. Then we have initial here you can read also called the outside the boundary layer. This is called potential. Okay, this is the potential outside the boundary layer. And here you can see same thing. Here it is stationary boundary and flow is flowing from this direction, and this is the variation of velocity. So here you can see flow is very fast, laminar, then some point transition, and then it will become turbulent, zigzag, very zigzag pattern. Okay, so these are defined by Reynolds number. Here is the laminar, very turbulent, and where is transition. Okay, so here you can see this is the transition zone, and this is decided by Reynolds number. And you can see these are the important reason here study is concerned. Here x is equal to 0. This is the called no slip condition. The surface of the boundary there is a region where there is no flow, and this is called no slip condition. Okay, so here you can see, and one more thing you can must remember, like laminar region is pure laminar, but turbulent region is not pure turbulent. It is the mixture of laminar and turbulent, because here you can see viscous sub layer. Okay, so this is the laminar region. Here viscosity effect is higher, and this happens because of the viscosity. Okay, and you can read all the data given here. And velocity is vary along the y direction, so you can see after some time, to some extent, it will become free stream velocity. And all the detail given here, and the same Reynolds number reviews upon nu is the kinetic viscosity, so it is compensated. So here you can see it is experiment flow, and this is the transition, and this will become turbulent. Velocity variation is here you can see the velocity variation region. Right, okay, here you can see after laminar sublayer versus the variation of the velocity. This is the boundary. Here the Reynolds number you can see for flat plate Reynolds number, critical Reynolds number 10 to 5, and Reynolds number earlier we saw the Reynolds number 2300. Okay, and this Reynolds number is for high flow. Okay, and this Reynolds number is for flow over a flat plate. Then see very different condition. Boundary growth along the curved path, as you can see the boundary growth along the curved path. We go from boundary velocity and pattern changes. So boundary types depend upon Reynolds number, which strongly influence the position of the suppressor. So Reynolds number is one of the important parameters for flow over a flat plate or to define laminar, turbulent, or transition. Okay. So here is the different formula. You must remember for displacement sequence, and if you want to derive, you can see the book and how to derive, easily can derive. And here, what is the displacement sequence? Like here is the definition. You can see can be defined as the measure perpendicular distance to the solid boundary by which the free stream displaced on account of the formation of the boundary layer. Okay, because the formation of the boundary layer needs some, like here is the viscous effect, and some energy will lost due to the viscosity. Okay. So this loss of energy can be compensated by the boundary layer and different type of momentum and energy thickness. So these are the, here you can see there are two similar terms called momentum and energy thickness. The momentum thickness is from the solid body by which the boundary layers would be displaced to compensate reduction in momentum due to the viscosity. Okay, and same reduction in energy due to the viscosity, because all this happen due to the viscosity. Okay? So you just remember small formulas like del shot displacement thickness 0 to del, okay, 1 minus u upon u infinity upon free stream velocity. And here this is not the this will not be mu, this will be u. Okay, so at the same momentum thickness u upon u infinity 1 minus u upon u infinity du. And here you can see this is the free stream, and for the boundary layer formation, and this has been, this would be equal, and by getting this equation you can calculate the momentum thickness. And so like that you can calculate energy thickness u by u to 1 minus u by u infinity bar into dy. Okay, here you can also see complete discussion of boundary layer theories beyond this book, and excellent. So this is not the complete analysis of boundary layer. Boundary layer, there is a huge big topic boundary layer, and one can write a book on boundary layer, and there are many books available on boundary layer, and you can read. If you go for higher study, you will see the different type of books, and on the boundary layer, and there are so many research going on the boundary layer and all this happen. And so for your concern, you just have to remember this small formula, and just basic thing, what is the boundary layer, how it is formed, and what are the parameter it has decided that this is the flow and turbulent transition and laminar flow. Okay. So just small things. Here is the drag coefficient. The drag force, here you can see drag for tau is equal to Cf rho v square upon 2, and same thing, F drag force Bl Cf square rho v square upon 2, where equal to the length and width of the plate. Okay. So here the thermal boundary layer. So what we see only the, in this book we'll see only the basic things as per this book. Okay. So as I have told you, the boundary layer is a huge topic, but in this book it is only given for just basic. Okay. What is thermal boundary layer? If see, fluid is flowing, and either plate are at a constant temperature or plate are at varying temperature. So according to those, temperature of the fluid will vary. If there is heated plate, like here you see the temperature variation. Okay. At the surface of the boundary, temperature is high, and as you go up, temperature will decrease. Here you can see. This is the basic thing, and this has been given by this formula. TW is wall temperature, T infinity is uniform temperature, fluid at a uniform temperature. Okay. So, and for the calculation, for the sake of calculation, theta has been given because temperature somehow vary in x and y direction. Okay. So this is also basic thing. Just remember, it is a variation of temperature. Like you can see here, as we go up, temperature of the fluid decreases, and at some extent it will become the free stream temperature. And also you can see here del T thermal boundary layer. Okay. Here, and it is defined on Prandtl number. For thermal boundary layer, Prandtl number is important parameter. Okay. For thermal boundary layer, thermal boundary layer, Prandtl number is important to know about what are the characteristics of this fluid, and what are the changes happen boundary layer, thermal boundary layer. You must remember Prandtl number, and here Prandtl number is not given more, and this is also important. You have to remember Prandtl number. Okay, so heat transfer coefficient, we already know this, convection and Newton's law of cooling, and temperature profile. Okay, so next, let me see something is important. Here you can see same formula we have gone through. Conservation equation of mass, momentum, and energy, and for laminar or flat plate. These are the derivative part, and I don't think you have to remember all this. You just remember these formulas. Okay, continuity equation for 3-dimensional steady state. So okay, for 2-dimensional, this dw by dz become 0. Okay, so no need to. I don't think you need to do it. Just remember this formula, and it will be helpful for your exams. Here you can see convective difference and local different d by dt. Partial differential equation. I don't think it's not important, so don't worry. You just remember some important formulas. You can solve all the. Okay. So del phi by del x, mu del square mu. If you can remember, you can also remember this formula. Navier-Stokes equation. Navier-Stokes equation, one of the important equation in higher study of. If you study in higher classes for fluid mechanics, so Navier-Stokes equation, Reynolds transfer theorem. These are some important things. Here is all basic thing I will give. So just study according to your syllabus. For compressible fluid, divergence of V is equal to 0. This is important. Conservation of energy equation also important, but as per your subject, I don't think this is important. But if you can remember this equation. See the energy equation. This equation is important. Here you can see the Prandtl number, nu upon alpha, and rho c upon k. Okay, so here, this is important. You must remember this. Here, mu c upon k. Here is important. Prandtl number. Remember it. Next, principal similarity of light. This is also a topic of higher study. For your subject and all the time, I don't think it's important because it's derivative part. So post convection, you can read here what are the given query, and here continuity equation del by del t plus divergence of rho v. This is the continuity equation. You have continuity equation, divergence of plus del by del t. Okay, this is the main continuity equation. Del by del t plus del divergence of rho v. It is equal to 0. That is the momentum equation, and that is the energy equation. And d by dx, del by del y, del by del z. You can see here this is the fundamental continuity equation, and this has transformed to this form because density is constant, and steady state flow, incompressible steady state, incompressible density is constant. So del by del t is equal to 0. Divergence of v is equal to 0. So this has become this equation continuity. Okay. Like this, momentum equation also has been changed to this form, and energy equation also changed to this form. So these are the same thing. These equations have been derived from this basic equation. So this you have to keep in mind that this is the main equation, and these three equations have been derived from the form of equation. Okay, we already studied this. Q barabar h d omega minus t infinity, and let me see some more thing. So Reynolds number we already see. Okay, Dirichlet number you have to remember. It can be asked on exam. Nusselt number HL by K. So and one more number, Prandtl number. Okay, so just remember this number, Prandtl, Reynolds, Dirichlet, and Nusselt. So these are important for your exam as well as your knowledge. So we see some here. Nusselt number is the function of Reynolds and Prandtl. So this is also important. Here you can see the free convection. So let me see some important thing. You can remember this Grashof formula, dB delta t L cube upon nu square. This is important. Okay, this will be directly will be asked in your examination number 5. For free convection, Nusselt number is the function of GRPR, and for forced convection, Nusselt number is the function of RPR. Okay, on a steady state heat conduction. So here this is the just formula, and you can remember if you want. Variation of convection heat transfer coefficient. So here are different method. Let me see if different method is given or not. Dimensions. You have to remember all this dimension because you are going to attempt the exam. And Rayleigh method. What are the method you can read if you want to study? But Buckingham pi theorem. This is also important for your if you're going to attend an exam. I think Rayleigh is important, so it will be directly asked. So for an example, so Buckingham pi theorem is important, so please remember, and you can read how to solve some fundamental dimension and pi terms. Here you can see number of dimensionless pi term n minus m, m minus n. M is fundamental dimension. Okay, so 5 minus 3. M is 5 variable, and L is n is fundamental number. Okay, so pi term will be 3 because, and this two term pi 1 pi 2 because 1 2 3 4 you can see here, and 3 fundamental, and according to this you can derive the dimension. ABC is equal to 0. So first see how many dimensions have been given in the your equation, like variable. You can see how many variables are given. 1 2 3 4 5, and this will become m. Okay, so variable is equal to m. How many variables have been given? So, and fundamental variable, we know the fundamental n. Okay, so pi term would be m minus n, your given variable minus fundamental variable. This will become the pi term. Okay, so and pi term again, pi 1 is equal to this, pi 2 is equal to this, and you just put the dimension of all the thing, you will get the answer. And after solving this, you will get the answer. So remember Buckingham pi theorem. Reconvection heat transfer, not important thing. Just remember plugin the Python comes from one. Here you can see grace of number and run detail. Delta L upon new square. And here an important number I think given. You have to remember some of the formula. HL by K coefficient, Eckert number, and the friction factor, Fourier number, alpha T upon L square. This is also important. Rayleigh number, GRP or Reynolds number will by nu. Okay. So that are some important number you have to remember. Means some other important thing. We've seen continuity, momentum, and energy equation in earlier topic. These are the derived energy continuity, momentum, and energy equation from that particular equation we have told you. Okay, so remember this equation. Boundary layer thickness is also in topic. So this continuity equation will be used for the derivation of the further boundary layer thickness. Here you can see also U20 by del. Okay, so you have to just remember not to write or memorize anything. This is also you can, if you can remember, just remember this formula will directly be an exam. These are boundary condition for the solution of this equation. And this is the formula for boundary. Okay, so del is equal to 5x upon under root r. This formula you should remember for the boundary layer. Del is equal to 5x upon under root r. Okay, so let me see some other things. This can also be remembered. Here you can see and conductive transfer. Let me see some other important thing. Not much important. Okay, so what we have told you, what we have studied, just remember we will see simple example for the solution, and you just practice, and you will be able to solve all the examples. And here you can see the different condition, velocity profile, and at that velocity profile what we will use boundary condition, what we will use the CF and B. So this table is important. This table important. You have to remember all the formula for the solution of the numericals. Yeah. So you remember this table for different cases. Here you can see the Blasius exact solution for that case, and 5x upon r2 and 1.328 upon under root r. Okay. This d is equal to boundary layer, and CF is the coefficient. You have to remember this. Based on the velocity profile, you can use the formula. Let me see some other important thing. These are just derivative part. What that you can study turbulent flow over flat and analog momentum. What is this? Anything? I don't think it's not important. For your this course. This is a topic for higher study. Okay, so for your graduation level, not need to remember, but and your completing young, they're not going to ask this formula like what are the value. Okay, so they will just ask the basic things and basic some formulas that you should have to remember. Constant heat flux boundary condition will not be. They are not going to ask anything about like this. There is boundary layer thickness, turbulent flow. These are the derivative part. Okay, we have studied this force convection inside tube. Okay. So here is the tube, and flow is flowing, and here is the formation of the boundary layer. That's it. Same thing. You have studied. Okay. From boundary to some extent, velocity will change and it will be constant. Now again it will decrease, and after that there is the hydrodynamic entry level, and after entry level it will become constant. Like here is the velocity profile. Fully developed flow. Okay. This is called fully developed flow. Here is the transition hydrodynamic entry level, and from here it is called fully developed flow. Here is the temperature profile in pipe in case of pipe flow. Here is the variation of temperature from here in this way. Here is the thermally developed region. Okay. And here if EW is greater than PR. Okay. EW is greater, temperature profile will look like this. Temperature profile will look like this, and it will become like this. Okay, if plate is higher than the plate of if pipe temperature is higher than the fluid temperature. So according to the temperature of the plate and fluid, thermal boundary layer will change. This is another things. Just know the basics. To know the basics of how it is changing, I think it is okay. Yeah, and there are other things. Okay. So you can remember these things, and hydrodynamic boundary layer 4 by 2 plus 2 okay. 4 upon 2 plus 2 hydrodynamic boundary layer. And some analysis of laminar post convection in long. These are the analytical part, and I don't think it's very important, but you can remember this formula. Maximum velocity occurs at the center of the pipe. R is correspond formula. So just remember, you can this formula and this formula, but this 32 L U upon D square. Change of pressure has a positive flow, lambda flow. This is called as a positive flow, pipe flow. Okay. So just upon R 64 by R F is equal to 64 upon R. This is also important. You have to remember this formula for numerical solution. This is important. Sometimes you will be asked that what is Hazen positive flow. So remember this. What is the Hazen positive pressure and flow? Constant heat flux. Let me see something at the right or not. These are the some these are the derivative part. Don't think, I don't think you much you have to worry about the derivative part. So you can, if you want, you can see the derivative how it has derived, and if you can uniform wall temperature in case of uniform wall temperature, what are changes happen, like how to derive and how the energy of Google flow lambda post convection. Continue to person become derivative so to del by del is equal to 0 in the case of Google flow. So these are the but we have to apply some boundary condition, and according to that, this continuous energy and momentum equation will change, and from this equation you can derive all the formulas and all the detail. But I don't think, as per your concern, there is a need to derive. There is no need to derive. Velocity distribution in turbulent flow through pipe. We can see velocity distribution. Okay. Analogy between momentum energy and turbulent flow. Center number. Okay. Empirical and is SD upon K. You have to remember and Nusselt number. Okay. So I don't think these are the liquid meter some cases, some particular cases, and for that particular cases, based on that, Nusselt number will change. And I don't think you have to remember so many Nusselt number. If you go in exam, you can be confused if you remember this type of Nusselt number. So just remember basic thing, and basic things will be asked in exam. Here you can see the coil case, Nusselt number, how Nusselt number varies, and all that. Flow across a single circular cylinder, post conductor, or external exterior surface, and here you can see the variation of the flow passing a circular cylinder. And you can see here CD drag coefficient F upon A rho is equal by 2. A is equal to surface area of this particular point. Okay, so this will be ideal. Let me see some other things. If important thing have been given, we can discuss. Otherwise, further we will go. Some here you can see the variation of Nusselt number for different cases. You need to remember important case, not to remember all that. It happen enhancement. Roughness tender. You can read all the detail what happened from that. And here you can see the different type of numerical, and we will solve here. You can see the continuity equation, and based on continuity equation, this has been solved. And momentum equation. Yeah. So that's three equation.